It's been almost 100 years since humanity first reached a revolutionary conclusion about our universe. Space itself doesn't remain static, but rather evolves with time. One of the most unsettling predictions of Einstein's general relativity is that any universe, so long as it's evenly filled with one or more type of energy, cannot remain unchanging over time. Instead, it must either expand or contract, something initially derived independently by three separate people: Alexander Friedmann, 1922, Georges Lemaitre, 1927, Howard Robertson, 1929, and then generalized by Arthur Walker, 1936. Concurrently, observations began to show that the spirals and ellipticals in our sky were galaxies. With these new, more powerful measurements, we could determine that the farther away a galaxy was from us, the greater the amounts its light arrived at our eyes redshifted, or at longer wavelengths, compared to when that light was emitted. But what, exactly, is happening to the fabric of space itself while this process occurs? Is the space itself stretching, as though it's getting thinner and thinner? Is more space constantly being created, as though it were filling in the gaps that the expansion creates? This is one of the toughest things to understand in modern astrophysics, but if we think hard about it, we can wrap our heads around it. Let's explore what's going on. The first thing you have to understand is what general relativity does, and doesn't tell us about the universe. General relativity, at its core, is a framework that relates two things that might not obviously be related. If your universe has nothing in it at all, no matter or energy of any form, you get the flat, unchanging, Newtonian space you're intuitively used to: static, uncurved, and unchanging. If instead you put down a point mass in the universe, you get space that's curved, Schwarzschild space. Any test particle you put into your universe will be compelled to flow towards that mass along a particular trajectory. And if you make it a little more complicated, by putting down a point mass that also rotates, you'll get space that's curved in a more complex way. According to the rules of the Kerr metric, it will have an event horizon, but instead of a point like singularity, the singularity will get stretched out into a circular, one-dimensional ring. Again, any test particle you put down will follow the trajectory laid out by the underlying curvature of space. These spacetimes, however, are static in the sense that any distance scales you might include, like the size of the event horizon, don't change over time. If you stepped out of a universe with this spacetime and came back later, whether a second, an hour, or a billion years later, its structure would be identical irrespective of time. In spacetimes like these, however, there's no expansion. There's no change in the distance or the light travel time between any points within this spacetime.